Alright, so today we're going to be doing 1.8, which is going to be arithmetic sequences. So before we do any examples, let's go through some vocabulary. There's three big S words we use in math: set, sequence, and series. Today we're going to be focusing on sequence. So sequence is numbers that are in a specific order based on some kind of pattern. Okay, so the pattern can vary dramatically. You can have all sorts of different patterns that exist. Okay. But the thing is, with patterns, some of them are specific and they are called arithmetic. So how do you determine if a pattern is arithmetic? Well, an arithmetic pattern will be always adding the same number over and over again in the same concept. So as you can see here, we've added 3 over and over and over again. They can also be adding a negative number, which would look like subtracting that number over and over and over again. Okay? So that's what defines an arithmetic sequence. And then a term is basically each number in the sequence. So if it's the first term, the second term, the third term, it's position. Okay, it's basically its position in the sequence. And then a finite sequence contains a limited number of terms, and an infinite sequence contains unlimited number of terms. So with a finite sequence, okay, it can end, it always will end, and it can end at like 1,000,000 or it could end at like 2. Okay, it can be anywhere that ends. And then infinite usually is infinite on one end but not the other. So like maybe it starts at 1 and ends in the positive infinity direction. And then the common difference is known as the constant number that represents the difference between the two consecutive arithmetic terms. So in this case right here, as you can see, our common difference would be 3 in this particular case. So that's how you identify it. So we will be doing domain and range as well. Domain is going to be based on what position you're in, and the range itself is going to be what the term is. So we use this notation, a sub 1, a sub 2, a sub 3. This indicates what term we're referring to. So let's go ahead and look at a few examples just to get an idea of what these things are. So the following are infinite sequences, meaning they go on forever in this pattern. So what do you notice the pattern is here?
3.
Good. And it's not enough to just check the first one. You need to check at least 3 of them to verify the pattern. Okay? So would this be arithmetic? Yes. And its common difference would be 3. Okay, that's an arithmetic sequence. Like I said, all sequences will have a pattern, but it doesn't have to be arithmetic. So if we look here,
This is adding all the odd numbers, right?
Technically, yeah.
7.
It's adding numbers of some sort. It's going up by 2 every time, right? Starting at 3, going up by 2. So yes, there is a pattern, but is this pattern arithmetic? No. So there is no common difference. Okay. So this is actually the pattern of a quadratic. Okay. Quadratic goes up by 2 each time. But once again, not arithmetic. It does have a pattern, but it's just not the pattern that we're looking for. So next one here, analyze the finite arithmetic sequence. So finite means that it has an end and a beginning. We can see the end and the beginning, but they ask us to fill in these middle terms here. So what is the common difference here?
2.
Not regular 2, but negative 2. So we always talk about common difference in terms of addition. So if you're adding a negative number or you're adding a positive number. If it's going down, you know you're adding a negative number. So what's the next term going to be?
4.
And?
2.
And? 0. Domain is going to be basically what position each term is in. So this is in the first position, the second position, third position, fourth position, and so on, right? So how many positions do we have? 7. Everybody see the 7 positions? And the range is going to be what fills those positions. So 10, 8, 6, 4, 2, 0, and negative 2. Now this is what we call set notation in math. And set notation doesn't have to be in any type of chronological order. It's just a bunch of numbers thrown in. Okay. Now typically you will see people rewrite them in chronological order, but that you do not have to. April with a capital A.
So would arithmetic sequences, would they be like a linear?
Exactly. Yes, they are linear functions. They represent linear functions. So we're going to actually see that happen right here. So x is going to represent the position like what position we're in, the first position, third position, so on. And this is going to be the actual term itself on the y-axis. So we're going to go ahead and graph the first 6 terms. So the first term is 10, so 1, 10. The second term is 8. The third term is 6. Fourth term is 4, and then you start seeing the pattern, right? So it's going to be here and here. That's the first 6 terms. And as you can see, when you graph this, it has a linear appearance, right?
Yeah.
And that's because of its constant rate of change. Okay, constant. The rate of change is constant, meaning it's going up or down by the same amount each time, which is what defines a linear equation. Okay, and you can see this one's going downward because it has a negative d value, right? So d is essentially going to be like your slope. So there's 2 different types of rules we use for arithmetic sequences. We have the explicit rule and the recursive rule. Both are useful for different reasons, so I'm going to talk about when and why and what you need to use for them. So for the explicit rule, you need to know the common difference and the first term of the sequence in order to use an explicit rule. The reason for using an explicit rule is, say I give you 3 terms of a sequence, or 4 terms, and I want you to find the 110th term. Now you could just keep going and either adding 3 or whatever your common difference is over and over again, but that's going to take a really long time, right? So that's when we use an explicit formula. It gives us right to the single term that we're looking for without doing all that math. Okay? Now a recursive rule is useful because it helps you find a current term using the previous term and the common difference. So say you want to know the 5th term, and you know the common difference is 3, but you know the 4th term. You can take the 4th term, add the common difference to it, and that will give you the 5th term, right? So that's what the purpose of the recursive rule is. So I'm going to be using these formulas on the next slide, just so you know where they're coming from. Excuse me. So write the explicit rule in simplest form for the following sequences. So when you want to write an explicit rule, you need to identify a sub 1, which is your first term, which is 6, and your common difference, which is what? 10. So everybody see where those 2 things came from. So the formula is a sub n is equal to d times n minus 1 plus a sub 1. N is like your variable. N is like your x. Okay? So a sub n is equal to 10 times n minus 1 plus 6. And this would be fine to leave it as if you were just going to use it. But this question asks for simplest form, so we're going to need to simplify this by distributing the 10. And then combining like terms, which is going to give me a sub n is equal to 10n minus 4, right? So this means that if you wanted to know like the 45th term, you would plug in 45 for n and solve, and that would give you that term. Does that make sense? Let's move on to letter B. So what is our first term in this sequence?
-1.
Good. What is our common difference? -3. Good. Everybody see why it's a -3? Because the numbers are going down, exactly. If the numbers are going down, you know that your common difference is going to be negative. Okay? So that's going to be a sub n is equal to your common difference times n minus 1 minus or plus your first term. In this case, it's minus because it's negative. So now we just use the distributive property. We get a sub n is equal to -3n plus 3 minus 1, which is a sub n is equal to -3n. Why did I write a 2 there? That was it's a 1.
Oh.
Plus 2. Anybody have any questions about that?
So if you need to find in whatever, in
Exactly. Way more useful than doing it out every time. So now we're going to write the recursive rule. So in order to write a recursive rule, you only need to know d. So what is d in this case? Positive 3. So the formula is just a sub n is equal to a sub n minus 1 plus whatever d is. And that's the only thing you put into the formula is d. So every recursive formula is going to look the same except for the d.
So how do we know, like, when we're supposed to do recursive and explicit, or just tell us?
No. So it's based on what you have, what information you have. If you know like the 5th term of a sequence and you want to know the 6th term, you use the recursive rule. If you want to know like the 45th term in a sequence, you use the explicit rule. So it's limited on what you know and what you have. So let's talk about what this terminology means. A sub n is the term you want to know. A sub n minus 1 is one less than the term you want to know. So if I were to want to know the 5th term, I'd have to know the 4th term to know that, right? To take the 4th term and add the common difference to it.
Wait, can you explain what a sub n minus 1 is? Yeah.
That's one less than the term you want to know, right?
Alright.
So if you want to know a sub 5, you have to first know one less than that, a sub 4, right?
Mm-hmm.
If you take the 4th term and add the common difference to it, wouldn't that give you the 5th term?
Yeah.
So that's what that formula is stating. I just gave you a random example.
That just seems like a longer way of doing it than like the explicit formula, right?
That's true, but sometimes you have to use this in more creative ways.
Okay.
So sometimes you don't know what the 1st term is, and that's when that comes into play.
So a sub n minus 1 is the number you want to know, like the number you want to know in the sequence of the one before that?
Correct.
Okay.
And then a sub n plus 1 would be the term after it.
Alright.
So what is the common difference in this one here? Good. And what is the 1st term?
4.
Good. So we don't really need to know the 1st term for recursive, I forgot, but a sub n is equal to a sub n minus 1 minus 5. So we have enough information to write the explicit rule for both of these. We're just practicing writing the recursive. So let's go ahead and try finding the 45th term of this sequence. So you could sit here and keep doing it, right? Keep adding the common difference, or we can write an explicit rule, right? So first thing to do to write the explicit rule is to identify the 1st term, which is
2.
And identify the common difference, which is
3.
3. Now we can write the formula. A sub n is equal to
3.
Good. Times n minus 1 plus 2, right? Now you could go ahead and solve this out, but we don't have to, right? Because it's not asking for simplest form. So what can we go ahead and do now? Plug in for the 45th term we want to know, right?
Yeah.
So you can just go ahead and plug in for 46.
Why don't you simplify it? Why do they make you simplify it?
Because there's good reason for it. If they want you to write it in a form where you could graph it like a linear function, because it's in the form y equals mx plus b. But if you're just simply plugging in, you don't need to simplify it, because you can just do the math here. So this is going to be 45 times 3, which is 135, plus 2 is 137. So how you would read this out is it would be the 45th term of the sequence. I'm sorry, I keep saying 45th. The 46th term of the sequence is 137. So if you kept adding 3 over and over again until you got to 147, or 46, you would get 137. Over and over and over again, you would get that. Any questions about that? Okay. So this is a situation where you're missing terms, so you can't easily just see what the difference is, the common difference. So I'm going to show you a trick that I use to find it. This is kind of like my own formula. This isn't like a thing you're going to be able to Google or anything, but this is just like the way that I usually do it. So you can find the common difference by doing the last term given minus the 1st term divided by the number of spaces between them plus 1. Now when I say first and last, I want to be very clear to you. First is the one that's directly next to the space. Last is the one that's directly after the space. If there was another term here given to you, you don't use that. You use the last one after the space. Okay? So like don't use the extras. There's a question on the homework like that, so I just want to mention it. So this is going to be 125 minus 80 divided by, how many spaces are there between the two numbers?
2.
So the bottom's going to be 3. So D is going to be equal to 15. So if the D is 15, what's the next term going to be? Good, and then? Good. Now I also would check and make sure that if I added 15 again, it would give me 125, right? Because that's just a way to verify that I did it correctly. So always then add the number one more time to verify that it gives you that final number. So there's always a way to check your work, which is really cool about this. So there's no reason you need to get something wrong when you can always verify that it's right. So let's go ahead and try this one. So D is equal to the last term after the spaces minus the first term before the spaces all over the number of spaces plus 1, which is going to be 2. So this comes out to be negative 17. Did we expect this D to be negative?
Yes.
Yeah.
Because
It went down.
it went down. So this next number is going to be 115. And then I would verify that I would then subtract 17 again and get 98, which I do. So always verify your work. Any questions about that? Okay. So the next question is going to be more of a linear model. So they are one and the same. So I just want to show you how they relate to each other. So in number 8, basically somebody makes $9 an hour and they're going to get a 15-cent raise every 3 months. So if they're going to be working for 3 years, we want to figure out what their current salary is going to be after 3 years. So how many months are in 3 years? Good, 36 months. And if you're getting a raise every 3 months, how many raises are you going to get in 36 months? 12. And if you're wondering where that came from, if I took 36 and divided by the 3 months, every 3 months I get the raise, that means that over a 3-year period, I'm going to get 12 raises. Everyone see how I came up with that number? Okay. So from here, we're going to go ahead and set up the equation for this. So, a few different ways you can set this equation up. You can set it up as a linear equation. Y equals the amount you get per raise times the number of raises you get, x, which we don't know yet. Well, we do, but we haven't plugged it in. Plus the current salary you make, right? Won't that give you your final salary? So, this is going to be y equals 0.15 times 12 plus 9, which will give you y equals $10.80. So after 3 years, you're going to be making $10.80 if you get a 15-cent raise every 3 months. Now the other way you could have went about doing this is to set up a explicit formula. So I'm going to show you a little bit how we would do that. So that would be a sub n is equal to your first term, which would be 9, right, the first term in your sequence, plus d times, what is our d? What is it going up by each time?
It's 0.15.
Good, 0.15 times n minus 1. Now what you would plug in for n if you do it this way would be a little bit different. N is going to be the number of times that raises that you have, right? So in this case, we said that 3 years is going to be 12 raises, but you're already starting at 9. So technically, if you're going to use this model, you're going to be plugging 13 in for n. Okay? So it's just two different ways of thinking about the problem. I personally think this way is a little easier for this problem to think about it, but I do want to show you how it also can be modeled in an arithmetic sequence way as well. Okay, so with arithmetic, you're always starting at 1 instead of 0, so you have to adjust accordingly with the n.
So where'd you get 13 from?
13 is like saying that this is your first, like you're assuming that this is already where you're starting at, is at 9.
Yeah.
So if you're starting at 9, then there's going to be actually, this is your first position. Then there's going to be 2, 3, there's going to be 12 after that, which is going to put you at 13.
Okay, I see.
It's confusing, yeah, that's why I prefer, this way is easier for you to like conceptually understand. But if we're having to use the arithmetic, I want to show you why that is 13. So I don't want you to get too confused by that or anything. It's usually pretty like intuitive. This topic I think is really intuitive. So you have some sufficient time to go ahead and get started on your homework.